speaker, Debin Gao, is currently an associate professor from School of Computing and Information Systems from Singapore Management University. So after obtaining his PhD from Carnegie Mellon University in 2006, Debin focused on his research on software and system security. And in recent years, Debin also actively participated in research of mobile security, cloud security, and the human factors in security. Welcome, Debin.
Thanks. All right. Thanks for the great introduction. My name is Debin. I'll be giving a talk on this work on the fine-grained Android application analysis. First of all, thank you for staying back on this very last session. Typically, we see fewer people towards the end of the conference or workshop, but I'm very happy that we still have the majority of the people over here. So thank you for staying back. All right, let's get started. Huge number of Android apps. I guess I do not have to motivate this too much. We all know that there are tons of apps out there. Maybe what I want to add on over here is that the apps are also getting bigger and bigger nowadays. In fact, the size increase is actually very steep, right? So that makes our analysis of the Android apps more and more complicated. Now, I want to spend a little bit more time talking about existing work in analyzing Android applications. First of all, there are static analysis tools out there, right, which is very comprehensively able to analyze the Android apps. But mainly the drawbacks about this is about obfuscation, right? So many apps are actually obfuscated, making it difficult for us to review the actual behavior of the app if you do not run it at all. Right, so that is the main drawback of static analysis. We want to actually run this app so that we can observe the actual behavior in case some of the behavior is actually, for example, encrypted inside the APK file. Right, so that is one main drawback of the static analysis. Cross-layer inspection, right? So when we say cross-layer, because Android apps, when they execute, they exhibit behavior under different layers. First of all, the application layer, right? So there could be the text code, there could be the native code, right? And it also interacts with the operating system, right? So when you make an API call, it gets trapped into the operating of the Android OS. So there are behavior exhibited with the Android framework as well. So in many cases, we wish to be able to analyze this cross-layer behavior, rather than just the behavior at a single layer, right? The next one is on emulation, all right? So there are many existing work that performs the analysis of Android apps on the emulator. Now, one drawback about performing such analysis on the emulator is that many apps may be able to detect the runtime environment. So if an app managed to detect that it is actually running on an emulator, it could potentially be stopping its behavior because it doesn't want its behavior to be analyzed. So typically, many of the malwares would do that. Many of the important, sensitive sort of like apps, government-related apps, they also do that as well. So we wish to be able to perform our dynamic analysis on the handset itself rather than on the emulator. Last but not least, fine-grained manner. Most of the existing work performs this analysis with the capability of analyzing at the API level, right? So library call level, for example. But what we wish to do is we wish to be able to perform at a finer grain at the instruction level and potentially also be able to analyze even at the registers or the field variable memory level as well. So that's what our objective, comparing to these related work in the existing analysis platforms. Right, so with that, I'm going to introduce our work on this fine-grained Android application analysis. It's an on-device solution, right? So it's not an emulator based. It works on the actual handset, right? It performs the analysis at a fine-grained level, at instruction level, provide capability of locking down even the register values and memory forensics. It also performs the analysis on cross layer. So it doesn't matter whether it's the DEX code, the native code, or when it traps into the Android OS. We lock down everything basically. All right, so here's my agenda. I will very briefly talk about the new Android runtime first. All right, so this is to introduce or to explain the challenges that we have in order to make it work on the new Android runtime. And then I'll explain our solution, and then followed by the evaluation. So I don't think I want to go through the details about here. Basically, the new Android runtime makes the dynamic execution of an Android app pretty complicated. Right, so we can see here that, okay, there are basically 3 different ways of executing code in our Android applications. There could be the traditional interpreter, right, the lower right-hand corner about that part, right? So typically when the app first installs onto our phone, right, so typically the first time when you execute it, it will go through the interpreter in order to do the execution, right? Now, after the app has been running for a few times, then a profile will be constructed, and then after that, the phone may actually be performing ahead of time compilation or just in time compilation, right? So that typically happens when your phone is idle. Let's say you're charging the phone, right? And then the Android OS will perform some ahead of time compilation, compiling some of the DEX codes into native code, even when your app is actually not running at that time, right? So AOT and JIT compilation would result in some additional native code being inserted into the AOT file, right? So then the next time when you start running the app again, it may not require to go through the interpreter again because part of the code is already compiled. So again, it's not my intention to go into the details, but I'm just trying to explain that this new Android runtime makes dynamic execution of the apps pretty complicated, and it's non-trivial for us to be able to capture every different way of the dynamic execution. So how did we did it? Right. This is the overall design of our work. All right. The left-hand side, the non-shaded portion, is the original Android framework. The right-hand side, the shaded version, is actually the newly introduced components that we have into the Android framework. So we have a few important components over here, including the bytecode tracer, the quick code tracer, the JNI tracer, and the native tracer. So in the subsequent slides, I'm going into a little bit more details into these 4 main components that we introduced into the Android system. Right, the first one, the bytecode tracer. The interesting part about this bytecode tracer is that Android already have a built-in profiler in this bytecode tracer inside the Dalvik runtime there. Now, the Android profiler has its originally purpose of being there. They are trying to build a profile about how the energy consumption is actually being affected by the code, right? So they will actually be able to tell you which portion of the code consumes more battery, consumes more CPU resources, etc. So that is the original intention of having an Android profiler. Now, what we did is that we actually looked into the code of this Android profiler and then add more capability to it. Now, specifically, what kind of capability are we adding into the Android profiler? It's about the handlers. So we look into every single handler. This handler performs not only just the method invocations, but also the branch transfers. So once we are able to capture or analyze these handlers, we actually modify them to add in our capability of performing our logging, be it when a method is being called and exit. Also including within the method, whenever there's a control transfer, we also manage to lock down the behavior. So that would allow us to perform this so-called fine-grain analysis, fine-grain tracing for these the bytecode executions. Right. So that is the first component that we have in the Android system. The next 2 include the quick code tracer as well as the JNI tracer. Now this one, what we did is simpler, right? Not as complicated compared to the previous slide, because here we are only performing the instrumentation for the entry and exit point of a method call. right? So here, we don't actually capture on the control flow transfers within a particular method. We are only capturing the entry and exits by performing instrumentations of these stubs. Very similarly, on the JNI chaser, we do the same thing. We are only instrumenting the native library loading process, so that whenever a JNI call is made, we will be able to capture and see which particular Java method or native method is actually being called. Right? Now, but you can see that if we just do that, then we will not be able to achieve our fine-grained analysis objective. Remember, we want to be able to perform our analysis at the instruction level, not just at the method invocation level. Right. So that's the reason why we need to have the last component here, and this is probably the most complicated one, is on the native tracer. Right. So this is a case where we already have the native code. The method has already been compiled. Right. So either is from Java compiled into native already, or it's actually a native library. Originally, it is already in native code. Right. Either case, what we do is that we perform the so-called on-the-fly instrumentation, on-the-fly rewriting of the instructions, so that every single control transfer instruction is now being rewritten into a trap into the kernel, into a system call. Right. So you can imagine that, okay, within this long piece of native code, right, if there is a control transfer instruction, it is being overwritten, being rewritten into a trap into the kernel, into a system call. And we provide our logging or tracing capability within this kernel component. So once it traps into the kernel, then we perform the logging, be it logging the actual instruction being executed, or we can also log the corresponding register values and memory contents. Once that particular tracing capability is done, then we return it back and then make the control transfer to the original control transfer target. So with that, then we will be able to perform the so-called fine-grained analysis. Right. So that is the native tracer that we have done. Right, so with that, then I'll just very briefly talk about the actual tool that we have. Right, so I'm showing two screenshots of the actual tool that we managed to build. The left-hand side one is about the end user will be able to select which particular app you are now trying to trace, you're trying to analyze. And after selecting the particular app, then we will also present to the user as to which particular classes, libraries that you want to perform the tracing. So there's a lot of configuration that can be done by the end user. You could trace everything, of course, right? Or you can also select to trace a particular shared library. In this case, for example, the right-hand side, there are a few shared libraries that you can select to perform the fine-grained tracing. All right, let me come to the evaluation part. The first evaluation that we perform is on the completeness or the correctness of this fine-grained tracing. So what we did here is that we compare the tracing result that we have with a source level solution that is in the market. All right, so this aspect J is another solution, but it actually works on the source code only. Right, so the app has to come with source code, and then you have to perform the static rewriting on the app. We compile the app, and then it will lock down every single execution when it runs. So, and that also is the reason why we perform this evaluation on open source apps, so that we can actually get the ground truth from this aspect J. Right. So we run this app with our fine-grained tracing, dynamic fine-grained tracing, as well as the log from this aspect J, which is the ground truth execution. Right. We compare them, and then we find that it's actually identical for most of the apps, except one of them. Right. So the last row here is the one that is actually obfuscated by ProGuard. Right. Now, when we look into the comparison, there is a one-to-one mapping between the logs from aspect J and the logs of our fine-grained tracing. But the method names are all different because of the obfuscation. Right? So this is something that we are expecting because of the obfuscation performed by this ProGuard. We also have two case studies to see how our system performed when we are trying to trace malicious software. Right? So this is one of the case studies. In this particular malicious app, what it does is that it performs some encryption and decryption on the strings before the strings are being used for Java reflection, right? So I don't think I want to go into the details here, but the fine-grained logs clearly shows how the string is being decrypted and then the corresponding Java reflection calls, right? So that enables us to review the actual behavior of this app. If you were to perform static analysis, then there's no way you can see this because the strings are encrypted and at runtime it's actually being called via Java reflection. A similar case study on a packed malware. We look into this particular malware. It performs pretty much very similar as to the earlier example, except that this one also dynamically downloads the DEX code over the internet, right? So the code is not even included in the original APK file. It is actually being downloaded during runtime. And then after that, it performs a decryption and then the Java reflection as well. And again, all these are being reflected in our logs. So this shows that our system is able to help us dynamically analyze malicious apps. Performance overhead, we are using this Geekbench to perform the to find out the performance overhead, and you can see that we have a few configurations to perform this evaluation. We have the first one, the stock Android OS without the our tracing platform at all. That is the very first baseline, right? And then we have a few configurations where we enable only Java invocation logging, or we also perform the logging on the third-party library, the native codes as well, right? So a few different configurations here. And you can see that the slowdown ranges between 21 to 33% when we are logging the Java methods. But the overhead goes to like 48% when we are logging both the Java code as well as the native code. So the performance overhead is actually quite high in this particular case. And again, this is also kind of expected on our case. Remember, number one, it is on a real handset. It's not on an emulator. So it is a pixel phone that we are using for this analysis. And also remember that we are actually performing very fine-grained level of the tracing, logging down pretty much everything, including all the control transfers, and sometimes in some of these cases, the register values as well. Right? So it does include quite high performance overhead. All right, with that, I'm concluding my talk. In this work, we propose a novel fine-grained analysis platform in a dynamic way. And it captures the application execution on multiple layers, right? So the DEX code, the native code, as well as its interaction with the Android OS as well. And we also show that it successfully analyzes complicated malware and provides a comprehensive view of this behavior. Although the performance overhead is relatively high in this case, it could go up to like 40-something% slowdown. All right, with that, I will conclude my talk and I'll be happy to take questions. Thank you.
Hey, this is Shubham from UC Merced. Pretty interesting work. One thing that you talked about is like it's a user app that you imagine to be used by the user. And you said like, okay, the overhead of the computation is pretty high. So do you think it would be better if like a company like Google, like who put the apps on the Play Store, would do this analysis beforehand, putting the apps on the Play Store?
All right, good question. As far as we know, Google performs their analysis in a scalable manner. You can imagine how many apps is being submitted every single minute or every single second. So that's why I think the majority of the study or the analysis that they perform is actually static only, right? Only if the app sort of like exhibits some or shows some malicious signs during the static analysis, would they then go into the more fine-grained or dynamic analysis. And that probably accounts to like less than 1% of. So I don't think this particular tool that we're proposing here is for such scalable analysis, but rather for a more targeted kind of analysis. You can imagine, for example, the banks, for example, right? So they let's say they outsource the development of their app, and when the app is actually being returned back to them, and then they would want to perform very fine-grained, very careful analysis before it is being revealed to the customers. So that is the kind of use cases that we are foreseeing.
All right. Thank you.
Thanks.
Hi, I'm Guyen from Yonsei University. So my question is that is there any room for malicious user? I mean the attacker to leverage this FA3 to attack this system?
Wow. Okay. Very good question. It's not something that I can think of for now, right? Main reason is because this is an analysis platform, right? So it is actually a dynamic analysis to be performed in lab. It is not really a system that an end user would use to perform this kind of analysis. So I'm not sure there is really an incentive for the attacker, potential attacker, to sort of like, I want to screw up your in-lab analysis platform over there. So this is the first part. I'm not exactly sure I can see that incentive here. And I'm not sure also what kind of objective they have, right? They won't be able to steal any personal information because, it is running in lab. It's not a real end user over here. So it's not something that I have thought about. That's why I couldn't give you a very good answer on this. But it is definitely an interesting question that maybe we should discuss a little bit more later.
Okay, thanks.
Thanks.
I guess we are running out of time. Maybe we can keep the discussion offline later.
Sure.
All
Thank you.
right. Thank you so much, Devin, for the wonderful talk.